1. What's the difference between average rate, initial rate, and instantaneous rate? An instantaneous rate is going to be found by getting the slope of the tangent of the plot of time versus concentration at any one time. So instantaneous rate is at any one point in time. The initial rate is going to be the instantaneous rate at time 0. The average rate is going to be the rate or the difference between two different times. So it's the slope of the line that would be between two different times or two different points. 2. Ozone decomposes to oxygen according to this equation here. So we're asked to write the equation that relates the expressions for the reaction in terms of disappearance of ozone and the formation of oxygen. Well, when we're looking at the reactants, we'll put a negative sign because that's the convention for disappearance. We need the reciprocal of the stoichiometric coefficient, the change in the reactant concentration over the change in time is going to be equal to, and this because we're on the product side now, we need a positive reciprocal of the stoichiometric coefficient, change in concentration of the product over change in time. Number 3, in the nuclear industry, we're looking at chlorine trifluoride, and we're asked to write the equation that relates the rate expressions for the reaction in terms of the disappearance of the reactants and the formation of the products. So we have our expression here. For the disappearance of the reactants, I need the negative change in concentration of the reactant because this one has a stoichiometric coefficient of 1. We don't have a reciprocal. The reciprocal of 1 is 1. And that is equal to the negative reciprocal of the stoichiometric coefficient of the change in the fluorine over the change in time. And that is equal to a positive now reciprocal stoichiometric coefficient, change in concentration of the product, I think I forgot a letter, over the change in time. Number 4, a study of the rate of dimerization of C4H6 gave the data shown. So we're asked to determine the average rate of dimerization. Now the average rate means we're going to take 2 points and analyze them. Here we're looking between 0 and 1600. So we need the average rate. Remember, the average rate is going to be rise over run. It's the slope. So you need to know that time is on the x-axis and the concentration is on the y-axis. We're told we need to look between 0 and 1600. In a case like this, it shouldn't matter which order you put things in. As long as you keep your point data together, you should be fine. And what I mean by that is if I put 0 first, then that means the y value for 0 needs to come first. And you know what? I'm going to put this in standard form. I think it'll be easier to read. So 1 times 10 to the negative 2 is just 0.01. And I'm going to truncate these just for brevity. So at 1600, I have 0.0504. Putting that all together in the calculator, I get an average rate of negative 3.1 times 10 to the negative 6. Now the units for this are going to be y over x, so molarity per second. So the other average rate that we were asked to calculate is going to be between 1600 and 3200. So again, keeping my y values together, looks like I forgot a 0 here. I get an average rate between these points of negative 1. I get a 0.04. I'm going to keep those values just for now. And again, the units are a molarity per second. Number 2, to estimate the instantaneous rate at 3200 seconds, then we need to have a graph. So here I've graphed it, and here I have inserted this tangent line. And now when I insert a tangent line, just something that I find easier to deal with is to extend that tangent line to my axes, because that makes finding the slope that much easier for me, because then I have the y value I'm estimating and they don't always work out as cleanly as this. So here my y value it looks like it is intersecting at 0.006, and then the next one is 0. So here I have an x value. I'm intersecting. I'm going to estimate that it looks just about 7,000, but it's hard for me to tell. So I need the change in y, which is going to be 0.006, over the change in x, which looks to be about 7,000. Now overall, this is a negative value, and this instantaneous rate, this is instant because it's the tangent, it's the slope of the tangent. This instantaneous rate is then found to be 8.57. I guess that could be 8.6 times 10 to the negative 7. Again, the units are molarity per second, and that is a negative value. Now we are asked to determine the average rate of formation, and it should be between 0 and 1600, and the instantaneous rate of formation. So we're looking at the other part here. So we have our reactant, so our change in reactant, and we can relate that to the formation of our product. So now we just need to insert the rates. So for the average rate, and again that should read between 0 and 1600, then I'm going to take this rate and I'm going to absolute value it. I'm going to make it positive because I'm forming, so I'm going to make it positive because that's the sign convention. So I'm going to take that 3.1 times 10 to the negative 6, and I'm going to divide it by 2 in order to get the rate of formation, because that is what's given here. So I have 1.6 times 10 to the negative 6, and again that is molarity per second. So for the instantaneous rate, again using the same formula here, if I put everything in the formula, then the rate of formation is found to be 4.3 times 10 to the negative, I think that's negative 7, molarity per second. Number 5, we have another graphing problem, so we get a little more practice here. So the first thing we're asked to do is to find the average rate of disappearance of A between 0 and 10. So the average rate, we're just going to find the difference between them. So here's my 0, here's my 10, and here's the data that goes with 0 and 10. And I find this slope, and this slope is going to be a negative 0.0375. The units are molarity per second. Now between 10 and 20, I can then insert my data, and I get a value of negative 0.0255, again molarity per second. Number 2, we're asked to find the instantaneous rate of disappearance at 15 seconds from a graph. So here I have graphed, and here I have inserted my trend line. No, not my trend line. I have inserted a tangent line. Do not insert a trend line. It's not going to help you. I've inserted a tangent line, and I did that by going to insert, and then there's symbols somewhere, shapes. Here we go. And I just used that function in order to draw in my tangent line. Now I prefer to draw a tangent line so that it intersects the axes. I find that much easier to calculate. So I have my change in y, so here's my instant. My change in y appeared to be 0.9, and my change in x appeared to be about 31. And I'm just doing the best that I can, and I get a 0.029 molarity per second. That's my instantaneous rate. For number 3, we're asked to find the rates of formation of B, and as we did above, so as A is consumed, we form B with a very similar equation that we had above. So for my average rates, I'm going to take the rate I was given, and multiply it by a negative half, or not the rate I was given, the rate I calculated, multiply it by a negative a half, and I get a rate of formation of 0.0188 molarity per second. That's my average, and for my instant, then I use my negative half, and this is negative. I take my instantaneous rate, multiply it by a negative a half, and I get a 0.0145 molarity per second. Number six is ever so slightly more involved. You just have to remember where your stoichiometry comes from. So if we're going to consider this reaction, we are given a rate of disappearance of bromine, and we are asked to relate it to the appearance of the bromine, the aqueous diatomic bromine. So I'm going to write, here is my disappearance of the bromine ion, the bromide, and relate that to the appearance of aqueous diatomic bromine. Now I am told at a particular moment I have this value for the disappearance of bromine. So I'm going to insert that number for this part right here. Now notice the stoichiometric coefficients are still there. So I need to multiply both sides by 3 in order to get rid of this so that I can tell what the change in or the rate of appearance of this product is. It needs to be a positive value because it is appearing. And I get a value of 2.1 times 10 to the negative 4 for this rate of appearance.